Then we start with you discussing this additive decomposition into a spherical deviatoric part. Last time I also mentioned that this decomposition is very important in mechanics because if you apply it to stresses, then we realize that the spherical part of a stress tensor and deviatoric part, they cause completely different responses in the typical materials, right? And spherical part usually cause volume change, especially for isotropic materials, and deviatoric part does not change volume, but it changes mostly the form of the material. That is why it makes sense, especially for small deformations, and it is done in classic, for example, in the classical plasticity theory. The stress tensor is decomposed in this way into a spherical and deviatoric part. What does it mean? This you see this notation SPH and DAV, and the spherical part is defined in the following way. We take a identity tensor I, multiply it by the trace of our tensor A, and divide by the dimension of the space. And correspondingly, deviatoric part is the rest. That means that it is the difference between our original tensor A and this spherical part. This is again here. It is then here. This is then a spherical part of a tensor, right? And you see here from the very definition, the spherical part also always has this form. We can also call spherical tensor, right? Spherical tensor also has this form. It is identity tensor multiplied by some scalar number, right? That is why for isotropic materials, like you apply hydrostatic pressure for opposite sides, and for isotropic materials, it always causes volume change. And again, we have this property. If you take spherical part of the deviatoric part or vice versa, it is zero, and you have to prove it. Zero tensor, you have to prove it at home. And for example, if you consider deviatoric tensor here, which is obtained in this way, then it is traceless. Trace of this tensor is equal to zero. There is a question in chat: is deviatoric always derived quantity like this? Yes, deviatoric stress is obtained in this form here. That means that spherical, it's a tensor whose spherical part is equal to zero, whose trace is equal to zero. This is the condition for a stress to be deviatoric one. And for example, we will discuss with you next semester in continuum mechanics the classical plasticity theory and yield function, and for metal plasticity, for example, yield functions always formulate in terms of the deviatoric part of a stress, because it is assumed that the spherical part does not produce any action, right? And due to the so-called plastic incompressibility condition. And that is why before formulating this yield function, yield condition, then we take this deviatoric part of a tensor. Very important condition from the mechanical point of view. So are clear? Questions? Okay, now I would like to go a little bit to show you outlook how we can work with other order tensors. So if you remember, we can say scalar values at zero order tensor, right? Vectors, we can say first order, and usual tensors, second order tensors, right? But we can continue, we can define other order tensors. It's only an example here. You see here in the next paragraph, we describe how the tensor. For example, if I would like to map a vector, not to another vector, but again to a second order tensor y, right? So I can do that by means of a third order tensor, right? This A is third order. You see also here the notation a little bit other. The font of this tensor is another one, right? And similarly, but without any definition for second order tensor, we define this tensor product here only illustration how we can define a third order tensor. It would be then a tensor product of three vectors, and we have here, this is important, that we have here three indices, and summation over the three indices can be original vectors, or it can be here dual vectors, or it can be mixture, you see here or here. Again, these dots are necessary because we need to specify the order of this vectors. Even here, you see, we need even two dots, right? In order to specify that I is the first integer, J is the second one, and S is the third one, and so on, right? But important is that, this is important here, maybe, that we can move again these indices up and down using this matrices Gij. This is the classical, what we see here, this is the classical definitions of in the tensor algebra. In the classical tensor algebra, such basis like he is not used, and tensors are, as I already mentioned, I suppose, tensors are defined as this values with indices, right? Third order tensor then has three indices, and if you would like to move down or to rise up these indices, we sum up the corresponding components A multiplied by this matrix G. You see here, in this case, we move one index up. Here we move two indices up, and here we move even three indices up. Every time some multiplying by this matrices G and summing up. And here the same, but we move it down, move the indices down. Here one index, two indexes, or even three indexes. There is a question. The dimension of the result of a mapping is always a difference. Yes, right. Yeah, not the difference, the sum. Or the dimension, maybe the dimension of the result, right. If you speak about this tensor here, it is second order tensor, it is a difference, right, in this sense. It is a difference between dimension of this tensor and this vector, right? So that means that here we have a third order tensor minus one, dimension of a vector, we have here second order tensor, right? Because maybe this may be important, because this this mapping is written in the tensor algebra, something like that. You have a third order tensor AI JK, and you sum up with the components of here xk, right? And what you get y, if you write it in terms of index form, right? In the classical form of tensor algebra. What happens here? Look, you sum up here over this index k, right? That means that you had initially three indices in this tensor. Take here again another color, right? You had here three indices. One is lost due to the summation, right? And then we get only two if indices free, right? Which means that the dimension reduces at one, at the dimension of this vector xk, right? What we have here, it is this simple contraction. What we mentioned already, simple contraction in the classical tensor algebra. I mentioned you, for example, in the literature list of the book. At the end, there is a classical book of Sokolnikov, and 50 or 50s, 60s of this last century. It's example, very good example of the classical tensor algebra. There are many application mechanics or relativistic theory, physics, geometry, many examples, and this basis, as I mentioned in the classical, is not used. The tensors and operation with them defined this way in terms of components, and this they call this operation simple contraction. And you see here we sum up over one index. That means that only two indices I and j remain free, and we get here then a second order tensor, right? 3 minus 1 is 2. Any other questions? So clear? When we are writing by hand, we note third order tensor by right. Yes, we will seldom use the third order tensor because they are seldom used in mechanics. We in the second part of this course and the next summer semester we'll discuss with you fourth order tensor. Why they because fourth order tensor we will underline it 4 times because fourth order tensors is a mapping of one second order tensor to another one. For example, strain to stresses, right? And this is then nothing but Hooke's law or any material law, right? And in this sense, this fourth order tensors are more important than continuum mechanics because these are elasticity tensor, compliance tensors, or tangent tensors. If you program a material law in Abacus, for example, by means of this subroutine UMAT, a user-defined material, then you need to program this fourth order tensor, and that is why we will discuss with you this fourth order tensors carefully in summer semester. And third order tensors are less important. So clear? Further questions? Please, we completed the chapter 1, and please do all this exercise to the end. We left some exercises, so everything here should be done. You see here, this is what this exercise I mentioned. Also, please do this exercise, calculating this Excel vector of this tensor W, also this this exercise 148, 140. So everything in all the exercises in this chapter 1 should be then completed. And today we start with the next topic, with the chapter 2, vector and tensor analysis in Euclidean space. Right, you remember we work there is one question, then a composition of 2 second, it is not a mapping composition. It is, what does it mean? It's not composition, not mapping. Composition is not mapping. Maybe we mean, if you say mapping, we mean mapping of vectors one to another one. But right, it is not a mapping, it's we call it composition, it's a matter of definition. But we can map one second order tensor to another one by a fourth order tensor, then we call it mapping, right? Because it's linear mapping. And right. Okay, first of all, maybe we stress that we work here within Euclidean space, right? With all these advantages, right? We have a scalar product here. We have orthonormal basis. You remember these features of the Euclidean space, and we work with both vectors and tensors. And analysis means that we will consider with you derivative. We will consider with you functions of this, functions of how these tensors or vectors and how these vectors can depend on scalar values. That means that these vectors and tensors can be also functions of other variables, right? And so-called fields, right? Fields where these values depend on some coordinates, right? If you consider a body, right? Some body and you calculate Cauchy stress, right? Depends on 3 coordinates, x1, x2, and x3, for example, right? And it's such a functions called field we will discuss with you. But we begin with you today with functions of only one variable. For example, time, right? Just imagine x, position vector of a particle can depend on a time, t can be time, or stress, sigma can depend on time, right? So this function are important, and before starting really with this function, we make some assumptions, right? Make some important assumptions. First of all, we consider with you continuous function. What does it mean? Maybe you remember it from classical mathematics, but we have to do it once more because we consider here not let's say conventional functions, scalar values, scalar valued functions, but we consider here with u vector valued. Such a function is called vector valued function, right? It's written here, tensor valued here, this vector valued, which means that the value of this function is a vector in the first case, and here for this function the value is a tensor. But they are function of real variable t, which can be, for example, time. Can be. Okay, continuous. What does it mean, continuous? If I consider this function x at t and fix some other variable t0, and then I take a difference, right? Can be some difference, but then what I do, I approach t to this value t0, right? And if I come closer and closer to it, the difference should be zero vector. That means that the limit of this difference between these two values of this function vectors at t0 should tend to 0 when t tends to t0. And the same is valid also for a. If I consider this different a at t minus a at t0 and consider this limit when t tends to t0, the result should be zero tensor. Such functions are called continuous. Such function called continuous, and this is from the very beginning we confine ourselves to a continuous vector and tensor valued function. So clear? Okay, the next point important, we also need differentiability. This function should be differentiable. And how to define this derivative of this function? Look, classical definition of the derivative, only instead of scalar values, we have here vectors, right? For a vector, or for tensors. For a vector, what we take this vector x function here, right? And add some increment here to the argument plus s. And then we consider the difference with the initial value, vector value of this function. And then we divide, because it's different, depends on this increment s, we divide by this value s, and then set s equal to 0. Classical definition of the derivative, but adopted to vectors. And this can be written also in this form, dx dt, derivative of this vector function with vector t. And we assume, of course, that such a derivative exists and is finite. And the same we do also for the tensor valued function, right? We again consider this increment plus s, takes the difference with the initial tensor value of this function, divide by s, and then consider limit case when s tends to 0. And this way we denote it by dAdt, derivative of this tensor valued function with respect to this variable t. Also assume that this derivative, this limit exists and is finite. Right, and written here, they are referred to as derivatives of the vector and tensor valued functions x at t and a at t, respectively. So clear? Okay. Once more, I'm recording this session, and if you have some questions, doubts, please write me in chat. Don't switch on your cameras or microphones. And right. We know a lot of differentiation rules, and for tensor valued function, we can define even more, because we have new operator. We have normally in the classical mathematics we have a product rule, for example, chain rule. But here we have different we have mappings, we have tensor product, we have scalar product, we have a lot of operations, right? And for all of them, these rules are mostly valid. And we simply look at this differentiation because they're very, very convenient for us, and we will do the following. We prove one of them, and you show how to do that. Right? We prove one of them using classical mathematics, only adopting this proofs to tensors or vectors. So, for example, first rule is the product rule of a scalar function with a vector tensor valued function. Just imagine that we have our vector valued function, but we multiply it by the scalar valued function u at t, and then we take derivative with respect to t. So the usual product rule of differentiation is applied here. We take x at t multiplied by the derivative du dt, and then vice versa. Take u at t and multiply by this derivative dx dt we just discussed with you. And the same is valid for this product of a tensor valued function again by this scalar valued function. Again, this product rule is valid, right? It is rather easy. Next rule is valid for mapping, right? You remember we introduced this mapping of a vector. We can map a vector x by a tensor, linear mapping, right? So our linear map. But just imagine both of them, both this vector x and tensor a depend on this variable t, right? On time, for example. And if you take the derivative, would like to take that, then we again apply this product rule of differentiation. We map x by the derivative of a with respect to t, and we map plus mapping of the derivative of x by the original tensor a, right? Scalar product, for scalar product also the same product rule can be defined. For example, we define with you scalar product of two vectors. Both of them can be functions of this variable t, and the same similar as we can formulate the scalar this product rule differentiation for the scalar product. We take scalar product of the derivative of dx dt by y, and then vice versa x at t multiplied by the just a second, small interruption. Okay, we continue now, right, and then this similar differentiation can be defined here. And the same holds also for the scalar product of two tensor valued functions. You remember we defined with you scalar product of two second order tensors, and a and b, for example, and they can be both function of a scalar variable t, and what we can do here again, we take the derivative dA dt, scalar product b plus a at c derivative dB dt, right? So clear? As I mentioned, we showed it without proof, but we prove one of them. One of them you will see here how to prove also other formulas, and we can only use these formulas in future simply, right? After that, any question, doubts? Okay, tensor product, right? You remember this tensor product, x tensor product y, and again we can imagine that both of these vectors x and y are functions of this variable t, and if you take the derivative, again nothing spectacular here, dx dt tensor product y plus x at t tensor product dy dt, right? And then we define with you also another operation, namely this composition of two second-order tensors. Both of them can be functional with variable t. And in this case, again, similar product rule is valid, namely, we have here in this case dA dt composed by b at t plus a at t composed by the derivative db dt, right? And this rule we will prove, I suppose, right, with you. Right, another important rule is the chain rule. Namely, just imagine that we have a vector function x of scalar variable u, but this variable u is in turn a function of another scalar variable t, and we need the derivative with respect to this vector function x with respect to t. Classical chain rule of differentiation is valid also here. We take the derivative dx du, you see here, and then du dt. And the same holds also for the derivative of the composed tensor varied function. Tensor A is a function of the variable u, which is in turn a function of another scalar variable t. And in this case, also this chain rule holds, right? And we can have also chain rule for a function of several arguments, right? For example, here x depends on two variables, u and v. Both of them are functions of the variable t, or tensor function depends on two variables, u and v. For example, u can be a horizontal displacement, v can be vertical displacement. Both of them depend on time, and x can be some other vector, velocity vector, can be whatever, some other vector. A can be tensor, and in this case, we apply the only difference you see here. We apply here the symbol which denotes here partial derivative. You remember that I for the you see here this means partial derivative, and still for the repetition, I once more wrote here the definition of the partial derivative. We have here derivative dx du partial, then this variable v is fixed. It's frozen, let's say, right? You see, if you look here at this definition, we add here this increment plus s only to the variable u, then take the difference with original value x, and then take zero derivative dy by s, and then consider s equal tends to 0. And the same is valid for a, right? Completely the same, only one variable u is varied, right? And another one, v is frozen. In this case, we speak about this partial derivative, right? And here you see we apply this partial derivative, namely here dx du, and here we take full derivative because u depends only on this variable t, right? And v depends only on this variable t, but the rest is the classical here, classical chain rule of differentiation for function of several arguments. So clear? Questions? So this rule, all these rules, you know, the equivalent of these rules, you know, from classical mathematics, and we only generalize these rules to vectors and tensors and to our products. Once more, we have much more products. We have scalar product, we have mapping, we have composition, we have scalar product of tensors, and all these operations should be then generalized. All these rules, differentiation rules, should be generalized to this operation. What I'm going to do now, I am going to prove this formula, this differentiation rule here, composition for the composition of two tensor varied functions, right? Here, this one. One of the most important, all of them are important, but one of them one of the most important is this composition of two tensor varied functions, and we try to prove it. How to prove it? The problem is that here will be the following. If we consider this derivative, you remember the definition of the derivative of this is a tensor second. This is what we have is second order tensor, right? Second order tensor, and the derivative of second order tensor is defined here in this formula, right? You see what we need. We need this increment. We add this increment plus s. And the most problem is how to express this tensor at t plus s, including this increment, right? And to do that, we define some arbitrary, some additional functions here. You see what I do? I take this increment here plus s of my function a, subtract here original function, divide by s, but do not take, if I take, look, if I consider this and take additional limit at s equal to 0, then I get exactly this dA dt, right? dA derivative, right? But now what I do, I subtract immediately this derivative and define a new function, right? Then if I do that, look what happens. Then the limit O1 of this new function I define at s tending to 0 is 0 tensor, because this term here, once more, this term will tend to this term here, right? Because you see here that we wrote if the limit of this term when s tends to 0 will be exactly this derivative. This derivative is here, and then that means that this term here, left term, will tend to the right term here in this difference, and that means that the whole function O1 will tend to 0. And the same, as you see here, the same we do for the tensor B, and we also define this new function O2 in the same way, such that the limit of this function is also 0 tensor. There is a question in chat. Can you explain rule 7 with an example? I do not understand the part of define as a function of u. 7 here. For example, okay, I have a very simple example. I have velocity vector of a particle. This is my particle, and this is my velocity vector, right? And this velocity vector, I can represent it with in two components. Maybe simple example, but this is the horizontal u, scalar. Maybe just a second. I will not write here. This is the horizontal displacement u. This and this is the vertical displacement v, right? So that means that I define unit vector here, e1, for example, and here unit vector e2. So I can write in this case, this is our vector x. So my vector x is an u e1 plus v e2, right? This is okay. This is my function. My vector x depends on two variables, on u and v. For example, in this way, what's the problem, right? In this case, x is a function of u, variable of two variables, u and v, right? Only an example, right? And the same way I can say also in here, I can say my tensor A can be, for example, equal to u e1 tensor product v e2, right? Why not? Tensor product, right? So I have a tensor varied function which depends on two variables, u and v, right? And A is a tensor. Only an example. More clear? Okay. So now we come to the proof, And look, so what we need to do, we first strictly apply the definition of this derivative. So this is our derivative of our composed function at t b at t. And how it is defined, we give increment, we subtract initial value of our tensor, divide by s, and set s tends to 0. And now the trick is the following here. I clean a little bit. Look what I do. I have this term here. This term here is here. This term is here, right? So what I do, I can express this term from this formula, right? How to do that? Look, this dA dt, I move to the left-hand side with plus, right? So I get then, I write here, O1 plus dA derivative dA dt. And then I would like, once more, I would like to express this A at this increment t plus s. Then what I have to multiply everything by s because I have here s in denominator. So I multiply everything by s. And then I should add here additionally this term, right? So this is then plus a at t. And this, what remains is exactly this a at t plus s, right? This is exactly what I need. And this a at t plus s, I insert here into this formula. That means this expression I insert here, right? And you look here, this exactly this expression here I insert. Only write out this. I write out this parentheses here s times O1 plus s dA dt is exactly here. You see s O1 here and s dA dt, and then plus the rest term is this a at t. And the same I do here with b. Completely, the only difference we have here is this function O2. This is this term here, this product. We subtract in original term here, and we divide everything by s. You see here, this is s here, and take this limit s equal, s tends to 0. Now, if you look what happens if you write out, you have here this expression here in the brackets here, this brackets here, and we multiply by this bracket. First of all, this term here times this term will be exactly the same term, and it is subtracted, this disappears, right? So then what we have here, we have this term here, a, multiplied by this two terms, and this is written here. This is written here. Then I multiply this b by this term here. Simply term by term, I write out this paramultiply term, I write out this brackets, and this is then this term here, second one. And we have additionally product of these two terms here. And you see the interesting, we have here s, and we have here s, we will have s square, but we divide everything by s. In the first case here, s disappears, and here you see instead of s square, we have s. So we have sum of two limits here, and you see the second limit disappears because we have s as a factor here, and s tends to 0. This is 0, right? And in the first limit, what happens then? This function O1 tends to 0, and the function O2 tends to 0 when s tends to 0. That means that if we write out these parentheses here, I clean a little bit again here. So we consider this term. So this product here, O1 with B will be 0. And this product, O2 with A, will be 0, right? So what remains? Remains two terms. This dA dt times B and dB dt times A. So this only these two terms remain. And this exactly proof this product rule of differentiation for composition of two tensor varied functions. So are clear? Questions? So this was a preliminary, let's say, paragraph which help us to work with these functions and to apply all the differentiation rules, because the derivative will be important. That this was how we understand this analysis, because as we discussed with you at the beginning, we are going to look how this vector valued function, how tensor values, they change with time, for example, or with other variables. And this is how we understand analysis of tensor and vector function. And the next topic is, I already mentioned, coordinates. Very, very important topic, coordinates. And we will discuss also fields with you, coordinates in Euclidean space. And another important topic, tangent vectors. I would like even to stress it more, tangent vectors, which are very important also in continuum mechanics. I mentioned already. We will discuss with you a large deformation in continuum mechanics. We will discuss with you different coordinate system in the reference, that means the undeformed configuration, deformed configuration, even if you introduce straight coordinates in the reference configuration, then they deform and becomes curvilinear in the current configuration, right? Due to large deformation. That means that we are required to discuss in continuum mechanics not only straight coordinates like Euclidean one, Cartesian one, but also curvilinear coordinates. First of all, let us begin with the definition. What is how do we understand the coordinate system? What is it? Let us look definition of the coordinate system. Coordinate system is one-to-one, is important, one-to-one correspondence. You remember we discussed this a little bit, but maybe I repeat. One-to-one correspondence means that we have one element in one set and one element in another set, and there is a connection between them. One element from one set corresponds to only one in another one, not to two, not to three, only to one, and vice versa. This another element in the second set corresponds to only one element in the first set, not to two, not to three. This is what we mean one-to-one correspondence. Between vectors in the n-dimensional Euclidean space, and very important, and exactly n real numbers, right? N real numbers, right? So that means that I have a vector in n-dimensional Euclidean space, and I get n numbers. Unique set of numbers, unique, because of this one-to-one correspondence, and vice versa. If I give you n numbers, you can give me a unique vector in this n-dimensional Euclidean space. So by the way, these numbers are called coordinates. This name n numbers are called coordinates of the corresponding vectors, right? And mathematically, we can express this definition the following way. So these are every of these n numbers, xi, x2, xn, is a function, unique function of our vector r. And this is exactly showing the symbol that is one-to-one correspondence. We can go in one direction, another direction. By alternative, we can say that our vector r is a function, unique function of these n numbers, right? N numbers, right? What is important for future also, certainly, of course, we assume that these functions here, all of them are sufficiently differentiable, because we will take the derivatives of this function, for example, in order to calculate this tangent vectors we discussed. So clear questions concerning this definition of the coordinate system? Okay. Example, and let's consider example, very important example, cylindrical coordinates in three-dimensional Euclidean space. Let us look at picture first, maybe it's better. So you see here what I do. I consider three unit vectors, you see, E1, E2, and E3. So we can always have such vectors in Euclidean space. This is the advantage of the Euclidean space in this case. And what we do here, right, we have a vector R, arbitrary vector R, and how I can express this vector? I can express this in terms of three coordinates. Phi, angle of this plane, you see yellow plane. The radius of the circle here, R, and also this vertical coordinate zeta. So if I make a projection of this vector R to this vertical axis here, I get this coordinate zeta. If I project this vector R to this plane here, to the horizontal plane, then I get this here length, which is this R, right? And then the angle between this projection and this axis x1 is nothing but this angle phi. And if I do it in a vector form, look what I can do. These are our three coordinates. Phi, we have three coordinates, angle phi z r. So I can write it also in this classical form here. I can, this expression consists of three components. Z is multiplied by the tensor E vector E3, excuse me, vertical vector. And here, this vector here is simply decomposed into parts. We take a projection to the we take a projection to this axis and the projection to this axis, and these two projections are obtained by means of the cosine, directional cosine phi and sine phi, and they are multiplied by this length of this vector r, and the here components. These are r cosine phi and r sine phi. Sine phi are components with respect to this basis E of the vectors E1 and E2, and the summation gives us this whole vector R. There is a question, could you please explain again the X as a function of Ri? Right here, simply if I take this, if I have this vector R, just imagine I have three-dimensional space, and we have this is X1, X2, and X3. And you get this vector R. You can always find the coordinates of this vector R, three values. For example, x1 Cartesian coordinates. We'll discuss with the Cartesian simplest case. Cartesian coordinates x1, x2, x3, right? They are unique functions of this vector R, right? For example, you project this vector R to this axis in three-dimensional space. You consider this vector as a directional arrow, and then you get these three values, right? And it can be generalized to any dimension, and we can define such a function also in n-dimensional space, right? Okay, so but if you come back to cylindrical coordinates once more, you see here, this is only one form. This is this second form. We need also this form. So we should be able to get our three coordinates, phi, z, and r, from our vector r. How to do that? For this value r, we apply simply this Pythagoras theorem, and we simply take a scalar product r E1, then scalar product r E2, and then we get here these two projections, and then according to Pythagoras, the square root of the sum of the squares is nothing but this diagonal in this triangle, classical Pythagoras theorem. The coordinate zeta is nothing but the scalar product, you can see it here, this value zeta here, right? It is nothing but this the projection of this vector r to this vertical axis, or we can write mathematically r times e3, because e3 is unit vector. Scalar product gives us the coordinate z. A little bit more complex is this with this angle phi, right? Usually, look, if I do the following, just imagine this is my coordinate system x1 here, x2, and this is my vector r, right? And this is my vector e1, this is my vector e2. How to calculate? I can calculate, if I calculate scalar product of this vector r by e1 and divided by r, this is, look, this is here r vector divided by this value r is a unit vector in this direction. I denoted simply by e, right? This is a vector e in the direction of this vector r. And if I multiply this vector e here by e1, I get nothing but cosine of this angle here, phi, right? Cosine. And then I can take simply r cosine function, right? And then get this angle phi, right? But there is one maybe non-uniqueness. We would like to get a unique function, namely, look, if we apply this procedure, but we have something like that. Look, once more, these are our axes, x1 and x2. And just imagine, I do the following. I consider such a vector r and such a vector r, right? The problem is that arc cosine defined, arc cosine is defined between 0 and pi, right? In this interval, right? It defines this interval. That means that if I have to this vector with the same angle here, alpha, let's say, right? This is our angle phi, but here I have the same angle alpha, then this we get a non-unique result. So that means both of these vectors r will give us the same value of arc cosine, right? And the problem can be solved if we consider another projection. We consider this projection of this vector r to this vertical axis. And that means that we multiply r by e2. And look, is it positive? Then here we are here in this half upper here, half plane here. I take another color. Then we are here in this half of the plane, and we apply usual course. But if it is smaller, then we are here below, and then we simply calculate this. We calculate this angle phi, and then take 2 pi minus this angle phi, right? And that then in this case, our solution for this angle phi is unique, and then we get exactly this unique one-to-one correspondence between a vector and this coordinates phi, z, and r. There is a question maybe why don't we consider x0 also in the set of zeros also a real number, or is it because of zero dimensional space? I don't quite get your question. What is the formula? You please specify which x0 you mean here, and which formula. I don't remember x0 today. Did we discuss 216? 216. Let me look. 216. It is here. I don't see any x0 here. Don't we consider x0 in the set of zeros also real? Yeah, okay, yeah. It's the method of definition. We numerate our coordinates simply beginning with 1. Is this I don't know what is what you mean, but we consider these numbers x1, x2, xn, and 1 going from 1 to n. These are our n coordinates. So you can if you want, you can begin with x0. x1, then you have here the last number would be xn minus 1, right? But maybe I don't quite get your question. It has nothing to do with zero-dimensional space. Zero-dimensional space is the zero-dimensional space. We don't consider zero-dimensional spaces. Even real numbers are represent a one-dimensional space, right? So for zero-dimensional space, we don't have any coordinates. I even don't know what you mean here with zero-dimensional space. Really. Or try to specify your question such that it becomes more clear for me. So clear this example, cylindrical coordinates, we will discuss with you later this example, also other details of this coordinates we will discuss with you, the tangent vectors, for example. But now I would like to consider other coordinates. Namely, there is important case of coordinates, namely so-called linear coordinates. Linear coordinates, I stress it here, how to define these linear coordinates. Namely, the idea is the following. Do you remember the very beginning of our course? And we said that components of a vector with respect to some basis are unique values, right? We prove it with you even. It was a second lecture. And this idea can be used in order to define coordinate, because we need this unique set of values, right? As you remember, the coordinate system is a one-to-one correspondence between a vector and set of this number. And this is the idea. I take a basis here, you see, I fix a basis h, for example, consisting of n vectors, h1, h2, hn. And then what I can do, I can say, okay, I represent my vector r with respect to this basis, xi, hi, right? And this is a unique representation. If I have these values, xi, I get, by means of this formula, I get this vector r, right? Uniquely. Vice versa, if I know this vector r, I multiply this vector I by dual vectors. You see this h, I with index I above are dual vectors. Then I get my components. So you see, this is unique definitions, right? From these values xi, I can always get my vector, and vice versa. If you know my vector, I can multiply this vector by the dual vectors h and get my components uniquely, one-to-one correspondence, right? And this means that in this way, we can define a coordinate system. And this coordinate system is called linear coordinate system, linear coordinates, right? And by the way, we come now to very useful and well-known example, namely Cartesian coordinates. Cartesian coordinates are special case of linear coordinates when we set this basis is orthonormal basis, right? So that means that we see here we represent our arbitrary vector r with respect to this orthonormal basis, and these are our Cartesian coordinates xi in this case. And vice versa, if I take a scalar product of my vector r by this unit vectors, I get the corresponding Cartesian coordinates. Very important special case of this coordinate system called Cartesian coordinates. So clear questions? Okay. Now we consider the following. Let us discuss two arbitrary coordinate systems, x and y. You see, these are two arbitrary coordinate systems, right? Which means that if I write in this way, I can also write the following. I can write r is a r is some function let's say with tilde of x1, x2, xn. And I can also write R is another function, R maybe with such symbol, another symbol, y1, y2, yn, right? So we can define two different coordinate systems. And now what I do is the following, namely, you see x here is a function, coordinates x is a function of R. And here I insert, instead of R, I insert this representation in terms of y, right? First idea. Second idea, here in the second represent, it was the first represent. In the second here coordinate system, I can, instead of R, I can insert this representation in terms of x, right? So which means that I have then two different possibilities. I can express, you see, if I do that here in the first way, I put here instead of R this way, I get this formula. So I can express my coordinates x as a unique function of other coordinates y. We call it coordinate transformation. Or in the second case, vice versa, I get my coordinates y as a unique function of coordinates x. So there is one-to-one correspondence between these two set of numbers, right? I have a look. I have this set of numbers x1, xn, and then I have another set of numbers y1, yn, and there is one-to-one correspondence. I get one, if I know one set of numbers, I can get another one, right? Through this vector r, they are connected to each other. They correspond to one and the same vector r, right? And now I make another trick. Look what I do. Look what I do here. This x here, you see, take another color blue. This xi, I insert into this formula. It's crazy, but in this way I can express y finally in terms again of y. You will see later why we need it. So this is what I do here. Look, yi is a function of x, but x themselves, that is why you see here another symbol, are functions of y, right? And so on. And why I do that? Because now I can take a partial derivative of this yi with respect to yj. These are completely independent coordinates. That is why the result is Kronecker delta. Only if I take dyi with respect to dyi, the same with respect to the same coordinate is 1. Otherwise, it is 0. And that is why I can write here Kronecker delta, right? But you see here from this formula, y depends on x first, and then x depends on y. So I can apply here chain rule of differentiation. If I take this derivative, I can derive first dy dxk, and then dxk with respect to dyj. And we see here k is here summation variable, chain rule of differentiation. Let me answer a question. Basically, in 221, we are represent same vector in two different bases. Not bases. 221, we represent 221 with respect to two different coordinate systems, right? For example, I have a vector r. I can take this coordinate system, Cartesian, but I can rotate them. So this is my x1, x2, x3, or these are Cartesian, or I can represent r in Cartesian coordinates, but I can represent r in cylindrical coordinates. It will be my coordinate y, right? So it is not the same base, are two different coordinate systems, right? Okay, so let us continue here and look here what we have. In principle, if I look at this expression here, we have here, in principle, matrix equation. We have on the left-hand side we have expression with two indices I and j, and here we have expression in which means that we have a matrix also on the right-hand side. Now, what I do, I take determinant on both sides of this expression, and here you see this delta is unit matrix. If I take the determinant of this delta, it is 1. And here I have take the determinant, but then I realize that this matrix here is a product of two matrices, this one and this one, because I sum up here over this index, second index here and first index here. We discussed with you already with this matrix multiplication in context of composition, for example, to tensor, which means that I can take the determinant of the first matrix and multiply by the determinant of the second matrix. And this is a very, very important result, which means that because these determinants are called Jacobians of this coordinate transformation, and we get the important result that this product of these Jacobians is equal to 1 here. And suddenly, not suddenly, but still, we proved with your theorem. Let us look at the theorem. If the transformation of the coordinate system, here you see this is a coordinate system, transformation of coordinates, excuse me, admits an inverse form, vice versa here. First, initially we have y as a function of x, and we can get inverse form of this transformation x as a function of y, then and j and k are Jacobians. These are this j and k here. These are our Jacobians. This is our j and this is our k, right? Then the j times k is equal to 1. Is equal to 1, right? Very important result for us for future, because also for us will be important that none of these Jacobians can be equal to 0, right? They should be different from 0. They should be different from 0, and you will see later today that this is very important for tangent vectors. Very important theorem. We remembered once more what does it mean, Jacobians. It's simply determinant, or Jacobian determinant is this matrix, and its determinant, it's written here, the determinant of the right hand side is referred to Jacobian determinant, right? Jacobian determinant. Okay, once more, if we have these two coordinate systems, then these coordinate transformations, they should have non-zero determinants, because the product of these two determinants in the direct coordinate transformation and inverse one, for example, for x to y and y to x, this product of this determinant should be equal to 1. And as a result of that, none of these Jacobians can be equal to 0. Why we do that? We see because now we are approaching this tangent vectors I promised you. And to this end, we consider now completely arbitrary coordinate system theta, curvilinear. Look, this is a definition. If I have a vector r, I can define my arbitrary coordinates theta I, or vice versa. I can, if I know this n numbers, theta 1, theta 2, and so on, theta n, I can calculate my vector r. So this maybe some, I showed maybe some way. These are my coordinate systems in 4-dimensional space, theta 1, theta 2, theta 3, theta 4. So for example, right? Curvilinear arbitrary coordinates. Now, I would like, look, you see, I somehow showed you with this curved line, I showed you this coordinate lines. But what is this coordinate line? How to define this coordinate line? Just imagine, let us look here and make it larger. I take one student here, some volunteer, and let the student go along this, walk along this coordinate line, theta 2, for example. How I can define, how I can be sure that the student does not go away from this coordinate, that he stays or she stays on this coordinate line. What is the condition for that? What do you think? Write me in chat your answers if you have some ideas. How to ensure that we are still, or students is still on this on this tangent should be followed, not quite, because if I go tangent line, then for example here I go away from this coordinate because it's curve linear. The condition is tangent at every point. Yeah, okay, but this is rather difficult to define with a tangent. All other coordinates should be fixed, which means that we should require that theta 1 is constant, theta 2 is constant, and theta 3 and theta 4. That means that all the coordinates should be fixed and only one is allowed to change. This exactly these coordinates we are moving on, right? And this is given here. Look, the equations here. Theta I is equal to constant value, where carefully I is going 1, 2, and so on, k minus 1. K is missing here, right? K is missing. We delete here k, you see, and then we go further k plus 1 up to n. So we fix here all the coordinates except to our coordinate theta k, and the result is a curve which is in a n-dimensional Euclidean space, which is called theta k coordinate line. Theta k coordinate line, right? And now what we do, we define tangent vectors. We mentioned already with you, vector tangent to this coordinate line. How to do that? Let us look at the picture here on the next page. Look, this is my coordinate line, theta k, going here, and I'm here in this point. How to define this? You see, this is tangent direction. I give, this is my vector r, which depends on these coordinates. All other coordinates, I don't write, there are other coordinates here, but they're fixed, right? They're fixed, I don't need to write them. I write only theta k. R depends here on this line. We are still on this line here, right? We are on this line here. And all other coordinates remains constant. That is why I write here r as a function of theta k. And now I give an increment. You see, plus s. So I jump from this point to this point. I'm here now, right? And the difference here, I define the difference is my delta r. But it's not tangent, right? How to get this tangent line? I decrease s. I say s tends to 0. Then I move here, I take another color, I move here, here, here. This is my delta r. Delta r will smaller and smaller, and finally my delta r will go along this direction here, right? And then if you apply this, but the vector becomes smaller and smaller, infinity is small. That is why we should divide this delta r vector by this value s. Both of them become smaller and smaller, and as a limit here, we get a constant, we get a not zero value, right? S tends to 0. And this exactly definition here, you see, we take this difference here, r at theta k plus s. This difference is here. This difference is our delta r vector, right? And divided by s. And then we consider this limit case when s tends to 0. And this is, according to the classical mathematics, nothing but derivative with respect to this variable theta k. I write here partial derivative, you see, because our vector r depends on many coordinates, and we change here only one. Once more, you remember, all other coordinates are fixed. And this is the result is the so-called tangent vector, the vector tangent to our coordinate line. And in this way, you see, I can go through all my coordinates and can define in this way, I can define n tangent vectors. I can define this n vectors tangent to all my n coordinate lines, right? This is very important that we have n vectors, and more important is that if these vectors are linearly independent, they form a basis in our Euclidean space, and this basis is very, very important. So let us prove that these vectors are linearly independent, right? You remember the theorem of the chapter 1, any set of n linearly independent vectors form a basis in n-dimensional vector space. How to prove it? We assume converse. Let us assume that these vectors dk are linearly dependent, which means that there are some scalars, not all zero, such that the sum alpha igi is zero vector. Right? And now let me do the following. I introduce here another coordinate here x. For example, linear coordinates. I take this basis h. Remember, we discussed with you, we said that if we define these coordinates x with respect to this basis, these are so-called linear coordinates. So I introduce this basis and calculate my linear coordinates, and then I can do the following. Look, I begin with this statement with assumption that this sum alpha igi is a zero vector, and here I use the definition. This is my definition of this tangent vectors, is derivative dr, partial derivative dr d theta I. But I have now another coordinate system, linear one, and I can apply here this coordinate transformation. I can first here, or chain rule of differentiation, not to get this derivative with respect to theta I. I can first derive with respect to my other coordinates, dxj, then dxj with respect to theta I, right? But these derivatives here dr here, take another color. This is nothing but my vectors hj, right? Linear coordinates, because look here, I come back to this linear coordinates. Yeah, this formula, clean a little bit. If you take the derivative here on both sides, dr dxi, what happens? You get exactly this hi, right? According to this formula. Here, this formula, right? And this is exactly what we use here. These derivatives here, blue encircled, is nothing but our vectors hj. So we get this result here, right? And you see hj, they form a basis, and we form here linear combination of these vectors aj, which is zero. It is not possible, right? It is possible only if all these coefficients here in front are zero. So we get this equation, namely n equations. All of these coefficients should be zero. We have n equations, and these equations represent a linear equation system with respect to this values alpha. And it is homogeneous equation system. But alphas are not all zero, as we said, which means that alpha represent a non-trivial solution of this linear equation system, homogeneous equations. According to mathematics, remember, a homogeneous equation system, linear equation system, has a non-trivial solution if and only if the determinant of this matrix is zero. But it is not possible. We just proved with you it's not zero here. If we have this coordinate transformation, we have it here. We assume with two coordinate systems, right? So this proves that this assumption is wrong. There are no such scalar values alpha, which gives us a zero linear combination of this our tangent vectors leading to this zero vector, which means that our assumption that these vectors can be linear dependent is wrong. It means that these tangent vectors are linearly independent and form a basis. Okay. So clear? Okay. I think it's enough for today. What we will do here, you see already, we will calculate with you tangent vectors for and dual vectors for this cylindrical coordinate. But what I would like to do, I would like to give you an additional exercise with spherical coordinates. Spherical coordinates are also very, very important. Let me show you this exercise, and then we stop here. Here you see there's a picture. These are spherical coordinates. There is a definition of the spherical coordinates, and you are asked to calculate tangent vectors, metric coefficient, and dual basis for the spherical coordinates, right? And we will discuss this solutions with you next time. So please complete the solve all this exercise of chapter 1, and also please do this exercise to 1 of the second chapter. And most of you I see then on Monday at this lecture find elements, but for other student who doesn't attend this lecture, we meet then in January, on 8th of January, the next algebra, I think it will be on 8th January. And you have a lot of time, a lot of time for the exercises. So I hope you will solve all of them and will be active next time. But most important, have a nice holidays and stay healthy, most important, at least until you get this vaccine, right? So be careful, and Happy New Year also for those of you who will not come on Monday to the lecture find elements. And then you still can ask me some questions if you have any. Write me in chat. Otherwise, then see you next year, right? And bye bye.